And with that, it's a pleasure to introduce our next speaker. Stefano Lottini. His talk is titled MLOps End-to-End Speedrun, Building an API Around a Spam Classifier Model. He is a developer advocate at DataStax with a strong interest in Apache Cassandra and distributed data systems in general. And his past work includes almost everything, I would say, from teaching to research to doing extensive work as a data engineer. So it's a pleasure to have you here with us today, and the stage is yours.
Thank you. Thank you, everyone. So it's a pleasure to see so many people after so long. Okay, today I'm going to talk about MLOps. In particular, this is a topic that has been coming up today several times. And it is not only made of technical aspects, but I'm a technical person, so I will focus on those. By the way, in the program online, I've seen the title. There was a typo, and it was called Speedrun. Many of you might have wondered what was that. It was just a transcription error, and sorry, maybe you were curious. It was just a speedrun, as in trying to squeeze as much information as I can in 15 minutes. So there we go. I'm Stefano. I am developer advocate at DataStax, where I work with Apache Cassandra. I'm the author of a plugin to use Cassandra from within the feature store Feast, which are sort of the main characters of today's talk. Previously, I worked at a company focused on trend detection through time series forecast with ML, and I can tell you that if it's true that you learned a lot by making mistakes, then I'm the most knowledgeable person in the world. So back to us, MLOps. There are various aspects about MLOps. Let's say that once you build your model and you train it, then the hard part starts. That is, as you've seen today, taking your model in production in a reliable way is not an easy task. So today I'm going to tell you the story of a fictional story of a company trying to put their application, their ML-based application in production. That's a sort of a parable going through several steps. And it is really a speedrun because the fictional story spans a few years, and I will try to make it into 10 minutes. So I have to say that the timer has not started as far as I see, but so I will try to just go as it comes. Okay, so the story is starting from raw data, building and training a model, then now it started. Then taking this model to production to power an application, so an API. Then, of course, you're never satisfied with your first model, so a newer version come out. Then there is the problem of versioning in the API. Maybe also at some point they decide to change the application architecture to make it more real-time or whatever. And then someone starts to speak of an actual real-time flow, which makes you change the architecture again. And you have to do this all by keeping compatibility and all that. So there are a lot of very practical problems all the time. And some of them are here on the right side of this slide. For example, in a big size company, it's a non-trivial problem to have a common place to retrieve and store and inspect features for your models. You need to have tight control over data leakage, over training, serving, skew issues, and so on. Of course, you need a storage backend. Sometimes you really have to do with big data, and your SQLite or your CSV storage might be not enough. So that's also a practical problem. You need to handle versioning in the API, and there are a few points. Now, before moving on, I want to tell you that you can have some homework from this talk, because I provide, and I will give you the link at the end, I provide a full GitHub repository for you to go home and reproduce every step in this story. So you can just clone the repo, follow the instructions, and you will have the chance to play with everything and have it run locally, all its microservices speaking to each other by yourself from scratch, just for the fun of it. Practice is the best teacher, right? Okay, so before starting, two main characters of this talk. One is Apache Cassandra. Raise your hand who knows what a NoSQL database is. Okay, so many of you, but not all of you. Raise your hand if you know what a database is. Okay, thank you. So Apache Cassandra is a very powerful NoSQL database. It's distributed, and it is made for very big data. So not only that, but it is able to deal with very big data. There was a question yesterday about how big is big data. The answer is, of course, very subjective, but Apache Cassandra clusters can cover hundreds of petabytes of data, no problem. So if your data set is big, then Cassandra is for you. Of course, it's not so easy to manage and operate, so that's why DataStax takes Apache Cassandra and makes it easily accessible as a service in the cloud. 2 clicks and you have your database to play with, as big as you want. The other very important friend in this story is Feast. Feast is an open source, by the way, Apache Cassandra also is open source. Feast is an open source feature store. A feature store is an important piece of a modern MLOps architecture, and it is exactly solves some of the problems I highlighted. A feature store is an abstraction over data storage engines that makes it easy to share features across teams in your organization, manage dependencies between features, versioning, and it helps to keep infrastructure and data very cleanly separated. In particular, Feast is based on the concept of an offline store where basically historical data is kept, a sort of a data warehouse. So Feast is not a database. It sits on top of various databases, but it handles the offline store as a time series data of all data that has ever been ingested. And then there is on the other side the online store, which is just where the latest snapshot of the data is kept for fast, low latency retrieval for online prediction and serving in production. Yeah, as I said, Feast can be connected with several backends. One of them is Cassandra, recently, thanks to the plugin. And yeah, so that's it. Now, let's go back to the story. So this is the very killer app front end that we have in mind in our company. We want an application that makes you look at your SMS messages, your inbox, and then there is a magic button that goes asking a spam classifier if the message is spam or not. And this is, of course, a separate service. So nothing fancy, but it is, of course, just a proof of concept. So first step, from raw data to the model. Now, there's nothing particularly fancy here. There is raw data in whatever form it is. Then we have developed a feature extractor, and we come up with 2 different data sets for later decoupling. One is the features, the other one is the labels. And these are stored, now in this case it's 2 Parquet files, but it could be anything more realistic, such as BigQuery, whatever. So this is something on which the offline store of Feast sits on top through these abstractions of the feature view, which are one-to-one with the actual data storage. And then there is this bigger box, the feature service, that essentially is an abstraction within Feast, and it represents a join between the 2 data sources. The point is that this join is made for you just by querying Feast. So Feast knows how to do everything. It is able to do point-in-time joins and to basically ensure you are doing your training on a time-consistent data set to avoid any kind of time travel issue. And this is done by, in this case, some notebook doing the training and coming up with a trained model that is then stored for later. Later means first production architecture. So we have the front end running, and this is speaking to 2 different microservices. One is a user data API, nothing fancy, but it is just reading from the table with your inbox data, which is stored in Cassandra, in AstraDB, for example, which is this big database. And independently, there is the model API, which is exposing the classifier, the feature extractor, or a combination of the 2, depending on the usage. Okay, so a bit more about the model serving, because then it is where the versioning comes in. So we need to keep versioning of the model in production all the time. We probably have to still be serving older versions of the model as they come out, because compatibility, whatever, accountability. So the models are served by a FastAPI application, which is a Python framework for API. And the FastAPI offers routers, which is basically an abstraction containing a set of endpoints that can be attached through separate, many times through different prefix. So we will have v1, v2, v3, / whatever the endpoint. And this is done by having a factory producing these routes, all in the same shape, ready to be attached to the API. And every one of these routes has empty sockets if you want to connect whatever classifier, whatever feature extractor to it. So there is the need for a common superclass wrapping the models, which are in general different. So as time goes on, the models get different. They have different input and outputs, but the interface has to be kept the same. And this is it for the API. Now, I'll go back to the feature store once more. You remember there are actual data, and then the abstractions that are the feature view, and they are sort of joined through the feature services. Feature services can also overlap. So to handle, for example, the fact that a new model might need different features. And now something even better comes out, because Feast has also other interesting features. Sorry for the word features used so much. Feast knows the concept of a push source, which means basically this thing here between the feature view and the physical storage. A push source represents the possibility of inserting data in real time, and then you just push data to it, like a new row containing the features for a new entity. And this will be propagated by Feast all the way to the offline storage and also the online store, ready for retrieval. That, combined with the fact that Feast can be also exposed as a web server, makes it for a very real-time way of inserting new data. So you just have to speak to the feature server, which is now an HTTP service, and the new piece of data will be propagated. You see these red arrows everywhere automatically. That makes it possible to devise a new architecture where an external agent, for example, the telephone company in this case, would just push a new message to the inbox, and everything else would happen thanks to APIs speaking to each other. So the inbox API reached by the telephone service would store the data in the user inbox, would speak to the API to get the feature, would speak to the feature store to store the features for later usage, so that then the user of our application will just click the button and the feature would be retrieved from the feature store and sent to the model for the final answer. Now, in the case of an SMS, this is maybe a bit contrived, but think of the case where the features are have to be previously computed, such as the pattern of usage of the users on your website, or the clickstream information, something that changes all the time. So this would be an architecture to just keep pushing new data, and the features would be there, ready to be retrieved and used in real time for example, recommendation. And that would be the final architecture, except some clever guy comes up with the idea of thinking of using event streaming instead of static databases. So in this case, it's Apache Pulsar, but it could be Kafka, whatever. So I don't think I have much time, so I will just mention that this would be just a stream of incoming data replacing the inbox API. And these can be also made maybe fancier with writing the data to the database and using CDC, so change data capture, which basically is an automated stream of all changes to the table, back to the streaming topic for later replacing the inbox API. The point is that here the behavior upon a new message is done by a pulsar function, or which is basically working as a serverless kind of thing, so you have even less dependency on deploying machines to do your bidding. So that was it, but since I've seen answers about NoSQL, I want to stress that by sheer coincidence, next week, here in Berlin, we will have Cassandra Day Berlin. So if we are interested in NoSQL, it's actually within walking distance from here, and that was absolutely coincidental. So you are welcome to join us for a day about NoSQL with a lot of interesting stuff. And I think with that, I'm done. Here you can see the link, so if you are inclined to actually play with stuff, please go there, get the repo, follow the instructions, and get to me if something doesn't work. I'd be happy to help you. So that's it. Thank you.
Thank you very much. Yeah, thank you very much, Stefano. Also, I love that idea that our speakers bring homework for the participants. So yeah, feel free to check that out. You'll also find the link on the follow-up presentations that will be uploaded. So if you haven't had the time to take a picture now, feel free to check that out later. We have a minute left for questions. So if there are any follow-up questions, feel free to raise your hand. And I see my colleague David is coming over with a microphone. Please quickly say your name and what company you're representing.
Does this work? Yeah. So hi, I'm Ralf, data scientist at MindPeak. And so since you mentioned the shift to an event stream database, maybe that's based on a real use case. So I'm just wondering whether signs that is a good idea to do for your application.
In general, it depends on the application, of course. But in most cases, it is because, well, there is no realer time than event streaming in general. So whatever kind of low latency database you can have, if you just keep pushing data to your data store, you have to either keep polling it, which is an, let's say, avoidable overhead, or you have to schedule a periodic update job. In any case, it's not as real time. So imagine you need to react as quickly as possible upon arrival of new data. So in that case, it makes much sense to have a real data pipeline. So events flowing through your application, and then maybe, of course, getting stored into your database, even just for historical purposes. Of course, you might be thinking maybe it's a bit of a brickler kind of architecture, because what if an event gets lost? Of course, that's, in a sense, the answer comes from your event streaming technology, which is resilient, distributed, fault-tolerant, whatever, in most cases. And then you probably, usually in a real case, you set up a retry queue. So everything that does not work is just put into a retry queue with a timestamp. So for ordinary retry. And if retry times get longer, then you get alerted and you have to manually do something. That's more or less the idea. In particular, I mentioned resiliency. In this case, what I'm thinking of is Apache Pulsar, which is, let's say, a modern, stronger Kafka, I dare to say. And this is an industry-grade kind of a streaming technology that is, again, replicated, fault-tolerant, and it has a few advantages over Kafka, I have to say. So, nothing against Kafka, but operations are a nightmare. Okay, that was it.
Thank you very much. We'll leave it here. Thanks, Stefano, for taking your time, and thanks for bringing homework and sticking around for questions, I'd say.